Monotonicity at a point. Hello everyone. To begin, let's recall that in our previous subsection, we focused on how a function behaves across an entire interval. However, in mathematics, it is often necessary to be more precise. We frequently need to describe the behavior of a function at one specific, single point, which we will refer to as x0. Now, before we move forward, it is important to realize a fundamental concept. The terms increasing or decreasing are essentially descriptions of change. Since change cannot occur at a single, isolated point, as there is no other value to compare it to, we cannot define monotonicity by looking at the point alone. Instead, we define the behavior at a point by examining a very small region, specifically an open interval, that surrounds that point. This conceptual foundation will lead us directly into the formal definition on the next slide. Formal definition. Now that we have established that change cannot occur at a single isolated point, let us move to the formal mathematical definition. First, let us set the stage. Suppose we have a real-valued function, f, defined on a domain, D, and we are focusing our attention on a specific point, x0, which lies within that domain. Now, let us define what it means for a function to be increasing at a point. We say that the function f is increasing at the point x0 if there exists an open interval, I, containing x0, such that the function f is increasing throughout the entirety of that interval. Similarly, the function f is said to be decreasing at the point x0 if there exists an open interval, I, containing x0, such that the function f is decreasing throughout that entire interval. To put this into simpler terms, imagine you are zooming in on the point x0. If you can find a small window around it where the function consistently moves upward or downward as you move from left to right, then the function is considered increasing or decreasing at that specific point. This conceptual window is what we will explore further using a real-world analogy in the next slide. Real-world analogy, the hiker's path. Now, to help you visualize the formal definition we just covered, let's use a real-world analogy. Imagine a hiker walking along a mountain trail. In this scenario, the hiker's height above sea level is a function of their specific position on that trail. Now, suppose the hiker is standing at one specific spot, which we can call x0. If we only look at that one single point, we cannot logically say whether the hiker is climbing or descending, because as we discussed in the first slide, change cannot happen at a single isolated point. To determine if they are actually climbing, we must examine the path immediately before and immediately after that spot, essentially looking at a small window or interval around them, just as the formal definition requires. If the path is sloping upwards throughout this small section surrounding the hiker, we can then say that the hiker is at a point where the elevation is increasing. Conversely, if the path is sloping downwards in that same small section, the elevation is considered to be decreasing at that point. This conceptual window is exactly what we mean by an open interval in our mathematical definition. Now that we have a conceptual understanding, let's move forward and apply this to an actual mathematical function in the next slide. Illustrative example. Now that we have discussed the formal definition and the hiker's analogy, let us apply these concepts to a concrete example to see how they work in practice. We will consider the function f of x equals x squared and determine whether it is increasing or decreasing at the specific point x0 equals 2. Starting with step 1, we simply identify our given components. Here, our function is f of x equals x squared, and the point we are analyzing is x0 equals 2. Moving to step 2, remember from our previous discussion that we cannot determine monotonicity by looking at a single point in isolation. Therefore, we must examine a small open interval surrounding our point. For this example, let us choose the open interval from 1 to 3, which clearly contains our point, 2. In step 3, we check the behavior of the function within this chosen window. We want to verify if for any two numbers, x1 and x2, within the interval from 1 to 3, the condition holds that if x1 is less than x2, then x1 squared is also less than x2 squared. To illustrate this, let us test some specific values. If we pick x1 as 1.5 and x2 as 2.1, we find that f of 1.5 equals 2.25, and f of 2.1 equals 4.41. Since 2.25 is less than 4.41, we can see that the function values are indeed increasing as we move from left to right. Finally, in step 4, we reach our conclusion. Because we have successfully found an open interval, specifically from 1 to 3, that contains x0 equals 2, and where the function is strictly increasing, we can formally conclude that the function f of x equals x squared is increasing at x equals 2. This step-by-step process demonstrates the neighborhood concept, which we will summarize in the next slide to ensure we avoid common pitfalls. Key takeaways. Now that we have walked through the formal definition and seen a practical example with x squared, let us summarize the core principles with these key takeaways. First, let's focus on the neighborhood concept. As we discussed with the hiker analogy, monotonicity at a point is not actually about the isolated point itself. Instead, it is about the behavior of the function within a small neighborhood, which is simply a small open interval surrounding that specific point. Secondly, let's look at the requirement of existence. To formally prove that a function is increasing at x0, you do not need to analyze every possible region of the graph. You only need to demonstrate that there exists at least one open interval containing x0 where the function is increasing. Finally, we must consider consistency. For a function to be considered monotonic at a point, its behavior must be consistent throughout the entirety of your chosen interval. This means the function cannot fluctuate. It must move steadily in one direction across the whole window. Keep these 3 points in mind, as they will help you avoid the common pitfalls we are about to discuss in the final slide. Common mistakes. Now that we have covered the definition and a practical example, let us move on to the final slide, where we will discuss some common mistakes to avoid. First, let's address mistake number 1, the idea that a point can be increasing in isolation. Some students often try to calculate the specific value of the function at x0 to determine its monotonicity. However, as we saw in our hiker analogy, you cannot determine if a path is sloping upwards by standing on one single frozen spot. Similarly, in mathematics, you cannot determine if a function is increasing or decreasing by looking at a single value. You must instead examine the behavior of the function for x values in the immediate neighborhood surrounding x0. Moving on to mistake number 2, confusing the point with the interval. A very common error is to state that a function is increasing at x0 simply because the derivative of f at x0 is greater than 0. While it is true that this is a very useful shortcut in calculus, we must be careful. The formal definition of monotonicity at a point, which is the core of today's lesson, is based on the existence of an open interval. To put it simply, the derivative is a powerful tool we use to check if the condition of monotonicity is met, but the derivative itself is not the definition. Always remember that the definition requires a small window of consistent behavior around the point.